All right, Physics 2, welcome back to part 2 of your lecture. All right, so we're continuing on with section 7.9. So we've been looking at the energy principle of using point particle models and now extended systems. Now we're going to throw something else in, which is how your reference frame matters. Energy accounting. So, as we've been talking about previously in physics, the point of the eye of the observer is important. So, we ask questions about what is in our system, what is in our surroundings, but we also ask questions about from what perspective are you observing? Are you observing from a perspective of rest, or are you observing from a perspective of constant velocity? And while the energy principle remains the same regardless of the observer, how you set up a particular problem will change based on these choices. So we've already seen how big of an impact system choice makes with our example of the cross racer and her bike and the earth. Now we're going to see about the perspective of a moving versus non-moving observer. All right, so let's consider a spring system, which we're very well familiar with. So a spring mass system. The spring has a spring constant of 525 newtons per meter, and it's attached to a wall with a mass of 3 kilograms, and it starts off at rest. So here we go. Then the spring is compressed to a stretch of minus 0.05 meters, so it's compressed 5 centimeters. And it's held at, that's an at sign, at rest. All right, then the block is released and it accelerates. And what we're going to look at for our final position is the point at which our mass is gone through the point where the spring is relaxed. So spring is relaxed, and the velocity is, of course, at the max. So this is our initial, and this is our final for all problems that we're going to be looking at involving this. All right, so speaking of problems, let's talk about how to analyze them. So our system would be the block plus the spring, leaving nothing in the surroundings. We've already discussed the initial and final state, so I'm not going to do that here. So this is our setup. All right, so we're going to be analyzing the setup both from a reference frame that's at rest, which will be very familiar, and a reference frame that is in motion. Okay, so a stationary reference frame. This is what you are used to. You're used to just standing there, hanging out, making measurements. All right, so you're watching this interaction. You are at rest. So you will view this, you'll view the spring mass system as though it were at rest as well. All right, so how much work is done on the spring mass system? Now we've previously derived this, but we'll just go through it again. So we know, looking at the forces on it, we know there's a normal force, We know there's a force of gravity. These do no work. They're perpendicular, therefore no work. Now you could ask, well, we know the wall, it has a non-zero force on this system. It's holding it in place with a force. But if we look at the force of the wall through displacement delta x, it's just force wall times 0, which is 0 because it's not moving through any distance. There's no work to be done. Okay, so no work. Let's do the energy principle. And let's solve for that velocity. That could be useful. Okay, so K final plus U final is equal to K initial plus U initial coming from plus work from E final is equal to energy initial plus any work done. Let's find some zeros here. Okay, so we end this where the spring is going through its relaxed stage, so that's 0. It starts at rest, so our initial kinetic energy is 0, and we just showed that work is 0. So remember, this is our starting and final times. Okay, so already we've got a much easier problem on our hands here. Fantastic. So we have 1/2 mv squared, which is equal to 1/2 ks s squared. We want to solve for v, so we have 1/2 3 kilograms v squared is equal to 1/2 525 Newton meters times 0.05 meters squared is equal to 0.656 joules. So velocity is equal to 0.33 meters per second. And of course, you just solve that by dividing both sides by 2 times 3 and then taking the square root. Okay, standard stuff. We know how to do this. We've been doing this for a while. Now let's kick it up a notch and look at a moving reference frame. Once again, these are the initial and final setup. So initially it starts at rest, and then the final state at rest and compressed, the final state is relaxed and in motion. Our system is the block and the spring. We have nothing in the surroundings. But now we have a moving observer. So a moving reference frame. All right, so here's our spring, and then you are moving, and you have velocity, or a speed, of 8 meters per second, so you're moving to the left. That is going to make this system appear like it's moving to the right. So from your perspective, everything moves around you. So it's like when you're on, if you have ever been to a city where there's a metro or an underground, and you're sitting in a train and there's 2 trains and you're looking out the window and you see motion. You don't know if you're the one that's moving or if the other train is moving, particularly if there's no acceleration for you to feel those kinesthetic sensations. So makes it appear like the system is moving 8 meters per second to the right. And so when we look at our final state, we've got a couple things to contend with. So we're going to have the whole system moving to the right with v equals 8 meters per second. And you're going to have this block. It's going to have velocity from the spring being in motion. We'll do that in blue. And it's going to have velocity from this also moving at a speed of 8 meters per second. And we're going to have to account for this. Okay, so let's start to set this problem up. All right, so once again, let's go after work. We already know the system, the surroundings, the initial, the final state. Okay, we'll start with the easy stuff. So once again, we have the normal force. We have the force of gravity. Work is for these are 0. They're still perpendicular. I mean, let's eliminate easy first, right? So now we need to go after the wall. So in the stationary reference frame, the wall did no work. However, we know that the wall is applying a force that is keeping the spring in place, and it's applying this force over a distance. And we can calculate the amount of work that it's doing. So a few things. So the kinetic energy initial of this is not going to be equal to 0. It's in motion. And so let's go ahead and go after the work from the wall. So once again, energy final is equal to energy initial plus any work done. This is what we're after. So kinetic energy final plus potential energy final is equal to kinetic energy initial plus potential energy initial plus any work done. Let's find some zeros. There's only one, still going through the relaxed spring length and its final state. This is non-zero, this is non-zero, this is non-zero, and this is non-zero. All right, so kinetic energy final is equal to kinetic energy initial plus potential energy initial plus any work done. All right, so moving on with solving this problem. So we've got K final is equal to K initial plus work. All right, so we have 1/2 mv squared is equal to, that would be v final squared, 1/2 mvi squared plus 1/2 k s squared plus work. All right, so let's plug in numbers. 1/2 3 kilograms times 8.33 meters per second squared. So that includes the 0.33 meters per second we calculated from the previous setup and the 8 meters per second that it's moving. So V plus V is equal to 8.33 meters per second. That would be, that squared's supposed to go there. This is equal to 1/2 3 kilograms times 8 meters per second, quantity squared, plus 1/2 525 Newton meters times 0.05 meters, quantity squared, plus work. And so we get work is equal to 104.08 joules minus 96.66 joules. Work is equal to 7.42 joules. So the wall is doing 7.42 joules of work on the spring mass system from the perspective of the observer. The energy principle still holds. We're just looking at it from a different perspective. All right, and if you notice, the stretch of the spring is independent of the reference frame. All right, so 211 on your own. Check this result with the work integral. All right, so moving along. I'm going to go ahead and get a fresh sheet of paper. We've got a new section, 7.10. Energy dissipation. All right, so we have talked about that the total energy of the universe does not change. So E universe equals constant, or at least that's the assumption that we make. All right, however, sometimes energy is dissipated into less useful forms. So what I mean by this, so if I push these papers across this, there's a lot of friction, and so some of that energy that I'm putting into pushing it is just getting lost to heating up the board, or heating up this thing that I'm recording on. And that's kind of useless. And so examples of, so what we call this is energy dissipation. Basically, less useful forms of energy. So some examples of this would be sliding friction, which I just showed you, air resistance, viscous friction. These are all forms of energy dissipation. All right, but there's one in particular we're going to focus on, which is air resistance. And this is something you all have practical experience with. So, drop a ball and a coffee filter. What happens? The ball goes straight down, the coffee filter floats down gently. I can do this with drop a ball, right down. Drop this, kind of floats. Now we know it's not the force of gravity. Force of gravity wants to pull them down at the same rate. It's air resistance. So air resistance impacts rate of descent on Earth. Now, if I was to do this experiment on the moon, we'd see something different. The moon doesn't have an atmosphere. All right, so let's start breaking apart what air resistance depends on. So air resistance depends on speed. So just an example, if you wave your hand back and forth, you're barely aware of the air resistance that it's going through. However, if you safely stick your hand out of the window of a moving vehicle, oh, you will feel air resistance. But, do that safely. All right, so let's think about how this impacts force. We know the faster it's going, the more air resistance you're going to feel. So let's say you drop a coffee filter. And you'll get a chance to do this. So here's our coffee filter. All right, so it's going to have the force of the air, which is going to be pushing it up, and it's going to have the force of gravity pulling it down, and the net force is going to be down. Now, as it continues to fall, you're going to see the force of it'll go faster and faster, so the force of the air gets larger. You have the force of the gravity, and then F net is a little less down. And then eventually, you're going to have the force from air resistance is going to equal the force of gravity, and so F net is 0. Now, using momentum principle, why is it still in motion? Because it was initially in motion, so it's going to stay in its initial state. All right, so what this air filter has reached is something called terminal speed. This is the moment when air resistance equals mg. So terminal speed air resistance equals mg. So the force from the air is equal to the force of gravity. All right, so in case you're wondering, for humans on Earth, terminal velocity, or terminal speed, is about 60 meters per second, or 135 miles per hour. And if you go skydiving, you could reach terminal velocity. So basically, that's as fast as you're going to go. All right. So approximately, there's other factors. Now let's talk about those other factors. So let's examine what else air resistance depends on. So let's say I've got the coffee filter that looks like this, and then I crumple one up into looking like a little arrow. Which one falls faster? This one falls faster. This one falls slower. So what we can see from here is that air resistance depends on shape. All right, so air resistance also depends on something else. So air resistance depends on air density. So if you're up in the mountains, there is thinner air than if you're at sea level, where there is thicker air, which makes sense. You know, we know that water is more dense than air, and you certainly feel more resistance in water than you do with air. By the way, this does actually make a difference as to what sports arena you are playing in. So if you are playing in a sports arena up in the mountains, balls go further than when you are playing at sea level. And yes, it makes a measurable difference. By the way, those of you who've not chosen a scholarly paper yet, that is fair game to present a paper on that. Okay, so this brings us to the approximate air resistance force. This is an empirical equation, means it's been determined through measurement. So the force of air is approximately minus 1/2 c rho a v squared v hat. So a is the surface area, rho is the air density, v is velocity, and c is the bluntness of the object. And you can see here, this is going to be the magnitude of velocity squared times the direction of it. And yes, air resistance does make a big difference in your daily life. If you didn't have any air resistance and you are a baseball player, you would be able to throw a baseball twice as far. Now, you wouldn't be able to breathe, so there would be other issues, but hey, at least you could throw a ball really far. Also, along those lines, speaking of baseball, so when you put spin on something, so you'll have a section of low pressure and higher pressure, giving you backspin. This is all due to air resistance. You can understand this using fluid flow. All right, so let's end this aside. Okay, so let's understand air resistance taking a particle perspective. So if you have a coffee filter and it's falling, you can imagine that since air gets denser, you're going to be hit several times at the bottom, a little less at the side, and a little bit, if at all, from the top. So you have all of these air particles that are pushing this filter up. That's what air resistance is. It is all of these air particles basically bashing into you, pushing you up. All right, so that wraps up my talk on air resistance, and we can move on to viscous friction, which is a great word to say, viscous friction. So basically, thick liquids and dense gases will impact the velocity proportionally to v instead of v squared. So before, when we'd been looking at the impact on friction, we'd been saying it was proportional to v squared. Now when you've got a viscous friction, it's going to impact it with a frictional force that's proportional to how fast it's going. So viscous friction in a mass spring system. So let's say you had a mass spring system in honey. This is what it would look like. You would start off and so on and so forth. So this is time on the x-axis. So the frictional force would be equal to minus CV, where C is a constant. And this is the frictional scaling constant. And so we can use this to update our analytical spring solution. So x of t is equal to AE to the minus C over 2m t cosine omega t. And then and this type of oscillator is called a damped oscillator. So for a damped oscillator, running out of room. Let's see. Omega is equal to Ks over m minus C over 2m quantity squared. And then from here we can see that in a case where there isn't much friction, omega is approximately Ks over m, which is what it normally is. So, and all of this is an example of energy dissipation, and we can see how, if you need to account for things like friction, how that impacts particular systems. All right, so that wraps up Chapter 7, and we're going to go ahead and start Chapter 8, which I always think is a particularly fun chapter. All right, so in this chapter, we're going to apply the energy principle to light. So let's talk about light. Photons. All right, so light is wonderful and incredible and mysterious with its wave-like, particle-like nature. So in this chapter, we're going to study light as a pure form of energy. So light is pure energy. And it is wave-like and particle-like. And we're going to be focusing on primarily the particle-like nature. So in physics, when we talk about light, we talk about the whole spectrum. So light is a spectrum. We see energies on the light spectrum within a particular range, but it's much broader than that. So let's look at the energy spectrum for light in terms of EV. So we can start out here. We've got 10 to the minus 6 EV. These are radio waves. Radio waves are a form of light. 10 to the minus 2 EV. We're dealing with infrared light. 1 EV. This is visible. 10 to the 2 eV. This is UV. 10 to the 4 eV, X-ray, and 10 to the 6 eV, gamma radiation. All right, so this is the spectrum of light. There's a much better picture in your book, but what I want you to think of light in terms of is energy differentiations and not just wavelengths. So the wavelengths correspond to different energies, and that's what we're going to be focusing on. So in terms of what we see light between 1.8 eV, which is red, and 3 eV, which is violet. So this is the range of light that we see. So another cool thing about light, so light is made of particles called photons. And these have only kinetic energy and are never at rest. They're always traveling. So you've got a packet of energy traveling at the speed of light. There is a photon, or an artist's rendition of it. All right, so if you recall, going back to our energy equation that works for everything, E squared minus PC squared is equal to MC squared squared. So for light, MC squared is equal to 0. Therefore, E squared is equal to PC, quantity squared, with momentum being equal to the energy divided by the speed of light. So Isaac Newton was actually the first person to think that perhaps light could be made of particles, but he wasn't able to, or this was not confirmed until the 20th century. So the 20th century confirmed the particle theory. Of light. And by the way, if you shine light through a prism and you see the different colors of light, I don't have very many colors here. This is an energy separator. True, it also is a wavelength separator, but remember, energy is related to wavelengths. So this is how we will be thinking about light as we move forward with Chapter 8. So this wraps up today's lecture, and I will see you next time for Monday's lecture. Okay.